let's talk about Planck's equation. You're going to see it on page 13, which is arrangement of electrons in the atom. Right, so here's our equation, which is Planck's equation. Right, so E is our quantum of energy. So you're asked to calculate the quantum of energy given, right, and you're given H, which is called Planck's constant. Right, and frequency, and of course that frequency refers to the frequency of electromagnetic radiation absorbed or emitted by the atom or the element, whatever we're referring to here. And based on these two values, you can calculate this quantum of energy. You may also be given the wavelength, and there's a relationship where if you're giving the wavelength, that you can still calculate this energy change, right? So we say that the speed of light is equal to frequency multiplied by wavelength, right? So this C here represents, well, what we call speed of light, and I'm not going to call it light because we're now expanding what we understand of light, which is visible light. And that visible light is one form of light energy. We have other forms of energy called electromagnetic radiation. So we're going to call this speed of electromagnetic radiation, which can behave both as a particle and a wave, right? And the value for C is equal to 3 by 10 to the 8 meters per second. So we can substitute into this equation to solve for frequency given wavelength or vice versa. Right, so this equation now becomes, right, this where we've inserted what is frequency, right, into our equation here. So Planck's equation can either be written, yes, like this, right, or like this, whether you're given frequency or wavelength. Right, and remember that E represents the quantum of energy absorbed or emitted by an element, right, where this quantum of energy absorbed or emitted is proportional or dependent on the frequency or even the wavelength of the electromagnetic radiation absorbed or emitted.